Okay, so we would like to talk a little about the notion of reflexivity in Banach spaces. Here pretty much what we have is that we start with a Banach space X, and we consider the set of all linear functional, meaning its dual space. So this is just the space of all bounded linear maps from X to R, which is a Banach space. And now we take the dual of the dual, so we call this the second dual. And that could actually make your head start spinning a little, because you have the space of linear maps from the space of linear maps. So it's something like this. So if you try to make sense of this, I think it's going to be a little hard. However, there is a natural map from X to X dual. And this map is the map that assigns to any X its evaluation on a functional. So I need to tell you what J of X of a linear functional is going to be. So this is supposed to be an element in the second dual. And this is simply X star of X. So this is in the dual. And it can be proven that this map is an isometry into X second dual, so J. Somebody might say, well, of all letters in the world, why am I using J? There's a special reason. It's a tribute to the mathematician R.C. James, who actually studied many things regarding the duality of Banach spaces. And he was also the one to construct a Banach space with some very amazing properties. But in any case, it turns out that this is an isometry, not necessarily onto. Not. However, if it is onto, then X is called the reflexive space. Then X is called reflexive. And you can think of it this way, that if X is reflexive, then this map is actually an isomorphism, and you can keep taking this map and it will still be an isomorphism, and so on. Whereas if a space is not reflexive, then this map is not onto, and then you can have a map into the fourth dual, which is again not onto. So in some sense, you can think of each of these spaces contained but not being equal to the next space. So we get a strictly increasing sequence of Banach spaces. Whereas if it's reflexive, this sequence doesn't give us anything new. And it can be shown that if it's reflexive, if X is reflexive, if and only if X star is reflexive. So the reflexivity is a very important notion. And out of the spaces that we have seen, it's useful to see which ones are and which ones are not reflexive. So all the LPs for P between 0 and, I'm sorry, 1 and infinity, are reflexive. And then pretty much all the other spaces that we saw, so C of K and L infinity and L1 and C and C naught, all these spaces are non-reflexive. Okay. And something that goes beyond reflexivity, it's a good idea to understand that there can be identification. So for example, LP star can be identified with LQ, isometrically identified with LQ, where of course 1 over P plus 1 over Q is equal to 1. It turns out that the dual of C naught is L1, and the dual of L1 is L infinity. So all of a sudden you have a very nice example of how C naught is immersed into L infinity, and certainly this map is not onto, because you have sequences that are bounded but certainly do not tend to 0. Okay, so there are some very, very nice things, and sometimes it's not that easy to identify the dual of a Banach space. So for example, for C of K to identify its dual, it needs a lot more work. It's the space of signed measures, but we're not going to go into that. So that's all we had to say about reflexive Banach spaces. Thanks for watching.